Today's webinar is going to be a mixture of some slides, some background, as well as a demo. And I'm going to start with the slides and background, and then I'll move on to demo. It's a very new area, large language models. We're going to talk about, as Lex mentioned, fine-tuning and retrieval augmented generation today, and how we can do that in Hopsworks. So Hopsworks is a platform for managing your data for AI. It also has support for compute and GPU. So we're going to talk about that as well today. But it's used widely at many large companies globally to manage data for AI. But we also have even customers today running LLMs in production. So Hopsworks as a data platform for AI, it's for managing your data for data science, for training models. It integrates with a lot of frameworks such as Spark, Python, Pandas, Flink, Beam, dbt, SQL for creating features. It also integrates with model serving frameworks, and it integrates with data discovery frameworks. But why we're here today, I think, is because in the case of the enterprise, many people understand that there is a competitive advantage by having large language models providing services to the users that are trained on the enterprise's data. So there are a lot of claims out there today saying that fine-tuning large language models on enterprise-specific tasks and enterprise data can perform as well or better than the largest of large language models, such as GPT-4. Now, this is just a quote that we're saying, making that point. And other companies are saying that the foundation models that we see out there today, such as Llama 2 and Falcon, can be fine-tuned, and that will be good enough for many enterprise use cases. So Alex Ratner from Snorkel says that there will be thousands of specialist models per organization, not one big generalist one, meaning GPT-4. So what we need are good quality foundation models that are open source, and then we can fine-tune them. And he's saying it's good enough. Now, the claim I'm making today is that it's not good enough. Fine-tuning will enable our models to speak the language that our enterprise speaks and our customers speak, but we also need context and history, because we want our large language models to be able to reason to solve problems, and also to personalize those large language models to users. And that's going to be retrieval augmented generation. So let's walk through an example of a service that you might build with a large language model. This is just an example of a large language model powered financial sales app, and we have a customer appearing here. So what we're trying to do, this is based on a conversation with a prospect that wants to build this. The customer comes in and said, I've just made some money from my AI startup. What should I invest it in? One of the challenges with financial products and selling them is you have to have deep knowledge of the products, but also deep knowledge of the market. So what's going on? And they're the two different parts. The products, we can fine tune our model to learn about the products available at this organization. But the market, that's external knowledge, and we'll use RAG for that, so retrieval augmented generation. So we can start. And the other main point I'd like to make today that we're going to say that I don't think any other people are talking about anywhere, and we're going to talk about the feature store in large language models, is that the starting point will not always be the query of the user. Here we can see that we have the user's query here, but we're saying customer identity. What we're going to talk about today is how the feature store will unlock enterprise data with user ID, with a session ID, with an order ID, with some form of identifier that can be in your LLM app that can be used to access the enterprise data. Because if your data is in a vector database and you have a string, yes, you can retrieve relevant documents, but that's not in a that's in a probabilistic manner, but it's not the best way to access your enterprise data. That will be with identifiers. So in this case, Linda's logged in, and we tell her we have some ideas. Linda says, I'm not really interested in property. I'm interested in something else. And then we go and use external data to say, hey, maybe you want to try these verticals instead, and the conversation continues. But basically, we need to use a combination of a fine-tuned model that knows about the products that this particular company are selling, but also be able to integrate with external data sources. For example, the history of what Linda has bought, that's enterprise data, but also what's happening externally out in the financial markets, and that could be a vector database. Okay, let's move on. So that's an example of a financial powered app. And like I mentioned already, we're going to have different parts. We'll look at how we can get an identity to unlock enterprise data with RAG and the feature store, fine tuning, and so on. Okay, so what can you do with large language models? I can't give this justice in a slide. What I can say is that people are looking at chatbots that I just presented there, summarizing data. You know, a lot of students use GPT-4 to generate content, and it's very useful for them. Information extraction is problematic because we have hallucinations. What I'm going to talk about today is LLMs as reasoning engines, where an LLM is given some text and it's able to reason out what the correct answer is. An example I'll give a demo later will be when a user logs into our retail site and they say, well, what happened? What about this product I bought recently? So it's natural language the user will use, but we need to find out what the products the user bought recently are. So we present the large language model with all the recent history of the user's purchases, and then the user's question, you know, what about this product I bought recently? And the LLM is able to reason out, this was the recent product you bought, and this is the answer to your question. So we're going to talk about reasoning. Now, reasoning is a very unclear term. The term that's used in large language models is called in-context learning. And what that means is that given a prompt, the input query or string that you write into your large language model, the large language model is actually able to learn or to solve specific problems with that data, with just the input data. It's an emergent property. So for example, LLMs are now able to do basic arithmetic, but you can see that this ability to do arithmetic, this red line here, the score of it only appears as the model gets large. And we define the model size by its parameter count. So you may have heard that, you know, Llama 2 is a foundation model, has up to 70 billion parameters. That's what we call the size of the model. And larger models have more reasoning capabilities due to the fact they're better at in-context learning. So these are emergent properties we can see. Now, there is debate about emergence and so on, but I'm working on the assumption that it's there. I've seen too much evidence for it to believe otherwise. So we're going to look at both of the problems that I mentioned. One is called fine-tuning of models, and the other one is called retrieval augmented generation. The large language model that we have here is a model of the world. So if you look at GPT-4, it's a model of language. You can ask it about questions about language. It does have some knowledge. It's prone to hallucinations. That's fine. But if you look at enterprises, and you know, many large enterprises have developed their own vocabulary. I know at IBM, where I worked for a very short period of time, or Intel, sorry, they have the Intel language. And you know, if you're playing computer games, we're working at a computer games company. For computer games, there will be a lingo belonging to that game. So if you can take that data that you have for your computer game and you can fine-tune the large language model, the foundation model, you can get it to sound like the people in your computer game. So fine-tuning on your private data will enable you to have domain-specific knowledge built into the model, and also be able to the language or responses produced by our model will be reflective of the data you've fine-tuned on. The other part that you'd like to do is to integrate external information, what you might call context, and real-time information. So information that appeared after the model was finished training. So we call that retrieval augmented generation. The idea is that we're going to get external data and we're going to integrate it into the prompt, the input that we put into our model, and then our model will be able to use that input data to reason about it to produce a useful answer. And the place where you are when you're doing both fine-tuning and retrieval augmented generation is called RAG-FT. So we're going to use the term RAG-FT LLM to refer to a model that supports both, that has been fine-tuned, a large language model that has been fine-tuned, and we're using RAG on it. And this is where we think you can create most value with models for enterprise data. Now, to get there, we're going to follow systems development abstractions. That means layering. Now, you don't need to have both RAG and fine-tuning in the same model. You can remove layers. You can remove fine-tuning or RAG here, but we're going to assume that we want all of them for the moment. So we start at the bottom layer, our foundation large language model that learns the model of language. Our fine-tuned large language model will learn for example, to speak like a lawyer if we train it on law documents. So to learn the domain-specific language, the RAG, or retrieval augmented generation, will enable us to personalize our model to the user who's making the query. So we present information about the user, and now the model can reason about that information and give a personalized response. And we're able to integrate into the enterprise data. So if our application up here, our chatbot, our natural language UI, has some key to identify that user, maybe they've logged in and we have an ID, maybe they've used it for a while, we have a session ID, or maybe they have a reference for a booking or an order they made, and we present that. That's the key that will unlock the access to enterprise data through the feature store. Now, most people who start on this will start at the very high level. You start at large language models because the cost is lower. So your large language enabled application is pretty straightforward if you use a model like a hosted model like GPT-4. And as you add the new capabilities for personalization with RAG and domain-specific language fine-tuning, this adds some costs. Training a large language model or foundation model is very expensive, so we're not going to go through that today. It would need it needs massive text corpuses, and there's many companies doing this. And luckily enough, there are many great open source foundation models out there. As I mentioned, Mistral, we're going to look at Mistral 7 billion later, but also Llama 2 and Falcon. So if you want to work with, let's say, GPT-4, you can obviously use it directly from your LLM-enabled application. And if you want to personalize it, then RAG, or retrieval augmented generation, can use data from a vector database or a feature store, and then you can use that hosted model over the network. If you want to further work with an open source large language model, then you should fine-tune it, and you want to fine-tune it with your private data. That data will typically come from a data warehouse or a data lake. And these are the services you will need to get working. We need data, your private data from a data warehouse, data lake, database. And then to do retrieval augmented generation, we'll need an external data source. And vector databases are very popular, but we'll look mostly at the feature store today. So why would you host your own large language model? Why would you fine-tune your own large language model? The most common reasons for this are for data protection. So you've got data sovereignty. Your data is not going to go to OpenAI. Regulatory compliance. You can also reduce the risk of model bias because you can introduce more guardrails when you're fine-tuning to ensure that the responses are not going to be problematic for your particular application. You can improve performance as well. You're not restricted to the response times available in a very large language model such as GPT-4, which can be a little bit slow. If you can have a smaller model that's fine-tuned on your data and works very well for your enterprise application, they can produce very fast responses. And also, you can lower your costs for training the models and doing inference. These models are large, and that's one of the main challenges, and you do often need GPUs for them. Finally, strategic benefits. If you can fine-tune a model in your data, it can give you a sustainable competitive advantage over your competitors who are maybe using an off-the-shelf GPT-4. Now, the main challenge I just alluded to there of building RAG-FT LLMs is scale. And scale means that we talked earlier about the emergence of reasoning capabilities in large language models with many millions of parameters. Foundation models can be anything from 10 to 500 gigabytes in size, and that means that they don't fit. The larger ones don't fit on a single GPU. So in Hopsworks, we can take a very large model such as Llama 2 with 70 billion parameters, and we can shard it over several GPUs for training and also for inference. So in training, you can use frameworks like Accelerate or PyTorch FSDP. For inference, we support Kserve, which enables you to allocate many GPUs to a single model. So this is very high end. The other challenge in building a RAG-FT enabled LLM is you'll need this external data. So where are you going to get the data from? So vector databases are quite popular. We'll look at the feature store today. And then finally, to maintain data sovereignty, you need to have your data. So you need, maybe you're on premise, maybe you're inside a cloud account, and you don't want the data to leave it. How do you manage that? So Hopsworks as a platform will help you solve all of these problems. So what Hopsworks gives you is we have a vector database and a feature store for RAG. We can do the scalable GPUs, and we'll talk a little bit about our file system as well, which enables you to get NVMe speed to your data, not just S3. So if you have a very large model like Llama 2 and S3, it can take 15, 20 minutes to load. So we can get that down to less than a tenth of that on HopsFS. And then finally, you'll need your open source models. And luckily enough, the best open source models, the best foundation models available today are also open source. So let's start with a little bit more detail on RAG and vector databases. This is the common use case that many of you will have seen before. A very common example of RAG when GPT-4 or ChatGPT started becoming popular was that ChatGPT was trained at the end of 2021. So it didn't know who won the World Cup in 2022. So what you can do with RAG is you can have a vector database where we write a data pipeline that reads data from Wikipedia, chunks up the pages. So you need to decide on the chunk size. Is it going to be a paragraph? Is it going to be the whole page? And writes those and use an embedding model to write those embeddings or vectors to our vector database. Now, when the user enters a query, who won the World Cup in 2022, we can take the same embedding model, compute the vector, go to our vector database and retrieve the most similar articles in Wikipedia compared to this query that I put in here. So it may produce, the article about World Cup in 2022 in soccer, but it may also, there may have been another World Cup in some other sport in 2022 that might have ended up in there because it's a probabilistic query. So assuming it gives us the right article for the World Cup in football or soccer in 2022, we add that as our prefix. This is our prompt template. So we put in the article from Wikipedia, and then we take the user's query after it, and our LLM will be able to reason that, oh, Argentina won the World Cup because I've been told in the prompt. So I'm doing in-context learning. This is pretty straightforward. Now, that's a pretty straightforward use case, but the more general use case, and you may have seen, there's LangChain is a very popular framework for this, is to build up maybe conversations consisting of several steps, what we call a chain. So maybe we have an input prompt and we ask one query, we get a response, and we have another question and we get another response, and then we get our output. And LangChain gives you good support for designing these prompt templates. And then you have your questions, and LangChain can have a retriever that goes to your vector database and asks the questions, and we get back. And that's great. You can do it for single shot, which is just one query, or you can have multi-shot where you have this chain of queries. So if we look at the more general case of RAG, when we don't talk about vector database specifically, we say, okay, the user issues a prompt, and then we have our chatbot here. It's going to retrieve data from some external store. It doesn't have to be a vector database. It doesn't even have to be a feature store. The data can be retrieved from any external source that we think might give us relevant context data or real-time data that's needed. And we're going to query with the augmented prompt. So we're going to have this prefix in our prompt in the prompt template, and then we'll issue the full query to our LLM. So moving back to the vector database example, so RAG is associated with vector databases because what we do is we can think of it as being a function. We have the input prompt. We go to the vector database to get similar documents based on the question the user entered. So we're assuming a chatbot here, the user enters a question. And then with that preamble we get back, which is the document, the preamble to our prompt, or the document retrieved from the vector database, we ask the LLM. Now, the assumption I made this point already is that RAG is RAG equal to only the vector database lookup on the prompt, or the input question. Is the input prompt the only available data to you that you can use for prompt engineering? So we have an application up here, and the answer I've given already is that no, we can also have other information that our application has beyond the prompt itself. So here I have an example giving us the user ID. So maybe the user has logged into this application and the user now has an identity. That identity is the key that will unlock access to enterprise data. And enterprise data in the form of a data warehouse, a data lake. Because we're doing this, our application is an operational application, you typically won't issue a query directly to a Snowflake or a Delta Lake, right? It's going to be too slow. They're columnar data stores. They're not designed for point lookups like that. So what we do in online AI applications currently is we typically have feature pipelines to compute or to take the data, the raw data in our enterprise data warehouse, and transform it into a format that can be queried with low latency from a feature store. So assuming we do that, we're going to replace the enterprise data with our feature store. What can we do? Well, we can take our user ID, we can use that to retrieve information that we think that our application here will think is relevant for the question the user is entering. And then we can build our prompt as the data returned from the enterprise data. This is our preamble or prefix. And then we add our question in there, and then our LLM will give us an answer. So that's what we're going to look at for the feature store. Now, the user ID is just one piece of information available to an application. It may be that you have users are not logged in, but they have a session ID, and we know what pages they visited and what data they've accessed. So we can retrieve other external information that's helpful to the prompt. Maybe the user isn't logged in, but they have a booking reference. You're probably familiar with this when you book a flight. You get a booking reference. Maybe you don't have an account on the airline, but you use the booking reference to retrieve your details. Excuse me. So let's look at the infrastructure we need to build this system. And if you have any questions, just write them in the chat or in the Q&A to clarify anything so far. So what you need to fine tune your LLM is you need some training data. And the feature store is the most common place where people or enterprises store training data for models. In the case of tabular data, feature stores are widely deployed. I think pretty much every hyperscale AI company builds their model training infrastructure on a feature store. So the way a feature store can be used in LLMs is that you can have feature pipelines that will take your enterprise data, and it may compute tabular data here. We'll have features with tabular data. We can also have unstructured data, and we can even compute embeddings on documents and even store them in the feature store. And once that data is available, we can use that as training data we can go to the feature store and ask for a consistent snapshot of training data and train our model. And I'll show an example of that later on. And then the training of the model will be fine-tuning a foundation model, and the output will be a model that we'll need to store in a model registry somewhere. So one of the challenges that I mentioned before is scale. So in most model registries, you have a REST API to upload your model. Now, if your model is 250 gigabytes in size, like if you're using MLflow, that's not going to work. So what you need to do is have an efficient way of storing models in a model registry. And what many people would do is, well, I'll store it in S3. So in Hopsworks, when we register a model with our model registry, it'll store it in Hopsfs, which ultimately stores its data in S3, but we'll see that we have NVMe performance access to it because Hopsfs is a cache for the data in S3 ultimately, a consistent globally consistent cache. Right, at this point, there is a question. I'll just take the question. So Rishkant asks, if we're fetching the answer for similar documents in the vector DB, is the use of the LLM here just to write the answer in proper sentences? Also, yeah, so the answer there is if you're fetching similar documents to the prompt, remember they're similar to what? So the question is, it'll be similar to the prompt is what most people would say. Then you get that as your prefix or the preamble to your prompt, and then you put in the actual question the user asked. And then the goal of the LLM is to reason and give you an answer based on that user input and what the LLM knows about language. Second part of the question is, if the answer from RAG conflicts with the LLM's historical knowledge, how does the LLM respond? So they don't conflict because the RAG is just producing more input to the LLM. So the RAG is just augmenting the input, which is our prompt. It's not the vector database in this case is not giving us an answer. It's just, excuse me, it's just augmenting our prompt. Okay, so great. So we looked at the offline architecture you need for, so you need GPUs, right, we go back here, sorry. So we need these GPUs to train the model. We need to get our training data. We can use a feature store to get our training data. The other thing that we might need is a vector database. So how do we get the Wikipedia articles into our vector database? Well, we need a feature pipeline again. Because Wikipedia articles get updated, we should run this feature pipeline on a cadence. Maybe once a month is enough, or once a week. It'll look at all the Wikipedia articles that have changed and then recompute the embeddings and write them to the vector database. And then the features, again, feature pipelines will update them, and we'll use that to update. An example I'll give later, it'll be retail examples, so users ordering products. But that's the structured data we're going to use in our input prompt. So we're going to have a retrieval augmented generation retriever, so a piece of code that retrieves data from the feature store based on the user query. So it's going to use the user's order ID or booking reference number to retrieve recent bookings, and then we'll use that as input to our prompt to help the QA chatbot answer the question that the user asks here, so get a better response. And this can all be built on top of a fine-tuned LLM. And like I mentioned before, they're kind of orthogonal. You don't need to have both RAG and fine-tuning together. You can do one or the other, or you can do both. So all of those three possibilities exist. We have another question here. So this is RAG-FT. What chunking strategies are generally followed? I mean, that's specific. Chunking is specific to vector databases, and I gave the example of Wikipedia earlier on, because we have unstructured data. So in our vector database, typically we'll have unstructured data. We might have PDF files, maybe from the company. So typical chunking strategies, like if you're using, let's say Llama 2, there is some support for computing the chunks in Llama 2. They have the code available for that, and you would include that in your feature pipeline. Now, some people use effectively hyperparameter tuning for these chunking strategies. They try different chunking strategies. Should I chunk by paragraph? Should I chunk by sentence, by document? And depending on the problem that you have, you may get better results for those. You very much need domain-specific knowledge to do that. There's no generic answer, I don't think. Yeah, so but for structured data, and we'll look at that later, this is just the standard feature store code. I have orders, I have products, and I can bring them from my enterprise data platform, my data warehouse or data lake. I'm just writing pandas data frames with features in here. And I can retrieve those again from my feature store with RAG as well. So I don't need to worry about chunking and the query. I'm not going to retrieve the data with the query. I'm going to use application-specific information like the user ID or the product ID. Maybe I get the user to enter their booking reference number here, and then I use that to retrieve the features here. Okay, so let's move on and look at how we build this. So you do need a lot of infrastructure. We've talked about that. And I'm just going to try and finish this one. Okay, we'll answer that one. So you do need a lot of infrastructure, we saw already. But you do have to write something as well. So what we try and do, at least with Hopsworks, is simplify what you need to write to three main parts: a feature pipeline, a training pipeline, and an inference pipeline. So your feature pipeline, as I mentioned already, it'll create, if you're doing RAG, you'll need to chunk some PDF documents or whatever you're doing. If you have structured data, you'll be creating the features for that. In the example I'll give later, you have just question for chatbots. We often have question response pairs for supervised fine-tuning. So we need to make that data available for training. So our feature pipeline is computing the training data, creating it from our raw data. Training pipeline will take the, in this case for supervised fine-tuning, we'll take, for example, for a chatbot, we might take question response pairs, train our model, and the model will be output, and the model, the new fine-tuned large language model, will make predictions with the input prompt and also the RAG data that we've retrieved at runtime. So we'll fill in a prompt template with the external data retrieved with RAG, but also we'll put in the user query in that prompt as well. So I mentioned already that Hopsworks has the main infrastructure that you need to both do RAG and fine-tuning. There is a feature store, there's a model registry, and there's a vector database. The vector database is OpenSearch KNN, so it has the classical indexing libraries like FICE. And you can see that the way you develop it is that you develop these three different programs, and then that makes up your complete system. You will, to have an app, you'll need to have some sort of user interface as well. I'm going to just use Gradio for user interface, a very simple example later, but that will make up your whole system. Okay. And then, of course, for enterprise, we will need to have logs, and we'll need to audit logs and Hopsworks does have support for feature monitoring coming in the next release. So monitoring of features and even predictions for drift and anomalies. Okay, now I mentioned earlier that one of the challenges is scale, and what you can see is that if I'm writing large volumes of data and reading large volumes of data, whether I'm writing a model that's 250 gigabytes or training data that's terabytes inside, if I'm writing to S3 on AWS, the throughput is not very high, right? So a Python process reading or writing to S3 won't get more than a couple of 100 megabytes per second. But modern NVMe hardware is orders of magnitude more performant. So an NVMe disk can now read and write at 7 gigabytes per second. I have one in the office here, which reads about 4 or 5 gigabytes per second. So what HopsFS is when we deploy it in the cloud or even on-prem and we connect it to an S3 bucket, it's a globally consistent cache, an NVMe cache. So you get, when you write to a file, that will be cached on NVMe disks. And when you read from the same file, HopsFS is aware of which node stores that particular file and the blocks for the file, and it can read directly from them. And it's reading directly from the NVMe disk. So we don't have any cache consistency issues, and there's no cache invalidation needed because writes happen through HopsFS. It is a HDFS API, but we'll see that we can also mount HopsFS as a local file system. So even then, when we're working inside Hopsworks, it looks like a local file system, but it's actually files stored and backed in S3. So we get the cost of S3, we get the performance of NVMe, and we get the benefit even of local files in our Python programs, which is really nice. So for example, loading Llama 2, we can get down to, with a really good NVMe disk, down to 37 seconds. This is 70 billion parameter Llama 2. And it's going to take nearly 1,000 seconds on S3. The other thing about scale is managing many GPUs. So if you're trying to train models with more than one GPU, it's a non-trivial thing. Llama 2 in particular, if you're fine-tuning for it, and let's say you have a DGX machine with 8 GPUs, first you need access to the data, and if it's an S3, it's problematic. But you need to also use all of those GPUs to train the model in parallel. So model parallel training with Accelerate or Deep Speed 3. So Hopsworks has support for this. And then the same is true for model serving. We support Kserve, where you can deploy these very large language models on many GPUs, and inference can be performed in parallel on them. So even models that don't fit in a single GPU, we can do inference on those. There's another question in chat that I'll take. No, it's just a comment that you can join our Slack. Okay, for model parallel training, this is where your model doesn't fit on a single GPU. What Hopsworks supports is it manages your GPUs. Hopsworks can run on the Kubernetes cluster, and the GPUs can be shared between teams and projects efficiently. Particularly in an on-premise environment, we will see that very nice support for sharing GPUs amongst teams and so on. For model serving, if you're using a large language model and you have a request response API, so it might be a chatbot, you might think, well, I'll use fast API, I'll run on Kubernetes, I'll make a container, I send an inference request and get an inference response. I mean, in a real enterprise system, it looks more like the following. Like I mentioned, Hopsworks supports Kserve built in. So Kserve is the de facto model serving framework for Kubernetes. But your inference request comes in, the users present text, we'll have pre-processing, which will involve RAG going to the feature store or the vector database. We may need to featureize code as well, and we may need to even, to compute embeddings over the input text to look up in the vector database. And then after pre-processing, we go to the model. If the model doesn't fit on a single GPU, with Kserve, you can use frameworks such as Triton Fast Transformer, which will does model parallel inference very efficiently. It's an NVIDIA framework. And then finally, when your response comes back, for a real industrial strength application, you need to make sure that the response is reasonable for your customers. So guardrails and filtering of responses are things that you might want to consider including in your LLM application. And then, of course, when models are being served, you need to have logs coming in so that you can observe the performance metrics and debug them in production. We have a question. So from an anonymous entity, what makes you decide to use OpenSearch Vector DB? OpenSearch is an embedding maximum dimension of 1024, but byte pair used by ChatGPT is mentioned 1536 and may not be accurate. So effectively, so we're supporting an open source vector database. Most open source vector databases, as you probably know, readers, they're based on there's a small number of very popular libraries. So I mentioned FICE, which is developed by Facebook. That's the most popular indexing library. There's also Small Worlds library as well, and then there's Scan by Google. So OpenSearch is pretty good because it supports two of them, the Small World Networks one and then FICE. It also has filtering, so you can insert data in there and you can add filters as part of it. And then of course it's enterprise grade. It supports security, and we have multi-tenant support for it in Hopsworks. There's a number of reasons why we're using OpenSearch built into Hopsworks. Of course, if you're on the internet and you want to use serverless Hopsworks, you can use your own vector database and integrate it with Hopsworks Feature Store. That's completely fine too. So I'm going to move on because I want to do a demo as well. So feature pipelines, as we mentioned already, we take raw data, we compute features, we'll have enterprise data available in the feature store, so structured data, unstructured data in our vector database, and we'll be able to use that. And Hopsworks enables you to write feature pipelines in many different frameworks. You can do it with batch frameworks if it's small data in pandas or even polars. If it's larger data, you can use Spark or dbt SQL. You can even use dbt BigQuery. We have an example for that. And then if you need very fresh features, you can use streaming frameworks like Flink or Spark Streaming, or even ByteWax if your data is not that big. For training, which is where we want to do our supervised fine-tuning, which is typically what we do, we're not going to do expensive pre-training. Often you can do full fine-tuning, but often frameworks like LoRa and QLoRa are used because they're basically adding parameters to your model along the different layers. And in the example I have, I fine-tuned Mistral with the alpaca data set, and it took a couple of hours, right? And it's not a huge amount of data, it's 50,000 samples. So if you have massive amounts of data and you want to do supervised fine-tuning, in the cloud it becomes really expensive. I have an on-premise server running Hopsworks here, so it's not as expensive for me. But often at the moment, fine-tuning large language models rather than doing full fine-tuning is often what many do decide on. And then the inference pipeline, I'm going to do a demo where we actually this is a sort of a classical case. I'm not going to do LangChain in the demo. LangChain is a bit overkill for what I need today. But a classical kind of demo or a system you'll see people develop is they'll have a user interface and something like Radio or Streamlit, LangChain to manage your prompts, and then the user will ask a question. We'll have our model being served on Hopsworks with Kserve. We'll do the feature lookups or the vector database lookups. Sorry, jumped around there a bit. We can do our post-processing, and then we can host our large language model there, and then we return our response. So this is kind of a classic architecture that you would have. I'm going to just show you now. I'm going to start by doing a demo of. I'm going to do a demo of a very nice example by Sebastian Raschke from PyTorch Lightning. So this example is actually the official starter kit for the NeurIPS LLM efficiency challenge. Now, it involves, I've mentioned, training on multiple GPUs. I'll show you multiple GPUs, but this particular example is just training on a single GPU. There's some code I output there. You can see when I trained this earlier, it took 35,000 seconds and 42 gigabytes of memory used. Now I trained it with QLoRa. So QLoRa is quantized LoRa. It actually requires more compute and longer training time than classical LoRa. So LoRa and QLoRa, unless you're familiar with them, are frameworks that enable you to train larger models on smaller amounts of resources, smaller amounts of memory and GPUs. Okay, I think I've answered that question. So yeah, we'll do that one done. So let's jump over and look at our example. So this is Hopsworks here. And you can see in Hopsworks, we have our feature groups, feature view, feature tables. We have compute support in Hopsworks. I have a notebook running here already. We have support for jobs. You can run jobs in here. We have a model registry. We have a file system in here. So this is HopsFS that I mentioned, and I'll just show you the code. We also have support for Git. So the way I started working was I cloned the repo. So we have this, this is the repo here, lit.gbt. So you can just clone it in here. And I cloned it into the Jupyter directory there. And, you know, I can work around, we can work with Git and Hopsworks. The libraries I needed to install, we have support for them here in Hopsworks. It's telling me to upgrade a version. I have PyTorch 2.1, we PyTorch Lightning, and there's a few other libraries that I needed in there. I think there was LLM I don't remember the name. Yeah, LM sorry, not LLM, and a couple of others. It's all located in this. This is the, here we go. I gotta move this 1 second. Yeah, this is the actual link here. So this is the code. This is the PyTorch Lightning fine-tuning tutorial, which is quite a good one. So it's using LoRa, as I mentioned before, and there's 6 different steps. So what I'll just show you is, you know, I cloned the repo, downloaded Mistral, and then converted it to the Hugging Face format. So there's a script there to do it, and prepared the data set. So it's the alpaca data set. Let me show you the alpaca data set before we move on any further. So this is my code in here. It's lit.gpt. This is the repo that I cloned. The data is in here. You can see here that the data, the HopsFS is really responsive, right? You know, this data is stored, ultimately can be stored in an S3 bucket, but it's still super fast. So this is the data set that I'm doing supervised fine tuning on. It's, we have an instruction, you have an optional parameter, which is called the input, and then you have the output that we expect the model to provide. So we do supervised fine training on it. Do we have an example with an input here? There is one down here further. Here, for example. So here's an instruction saying transcribe the recording into text, and then it says recording about the history of Waterloo. And then here's a very brief history of Waterloo. Now, this is, I'm sure, prone to massive amounts of hallucination, but that's the alpaca data set released by Stanford. Now, there's a lot more in here. I'll just show you briefly the output because I used LoRa merged, I think. Yeah, so we can see here, you know, I got a 13.5 gigabyte size model output at the end of using QLoRa. Okay, so let's have a quick look and on my notebook. I think was it this one here? Yeah, this one open. So this is I'm in my repo in here. So it's lit.gpt. And this is just standard Jupyter Lab. Many of you will be familiar with it. You can also open, so what's nice in Hopsworks, you can open up a terminal here. So in our tutorial here, it's not a notebook, right? It's just telling me to run Python programs. So we can do that in Hopsworks. I ran bash to enter my bash as my shell. And you can see I'm inside this directory. It's the same directory that we have if we go into the file system and look at it. This is the file system here. So it's this directory here, okay? Now, do I need this one? That's a different one. Could we close that one? So what I'm going to do is, let's do fine tuning first. So I have 2 fine tuning. This one here is, we'll zoom in a bit so you can see, hopefully. I'm in the wrong keyboard. There we go. It's too much. I've zoomed in. Okay, so hopefully you can see that. So this fine tuning is using 16-bit weights, and you can see it starts up here. When it's loading the model, you can see it's very fast to load quite a large model, which is Mistral 7. We can actually look at that model. I think the model's in here somewhere in checkpoints, Mistral AI. So we have it in here. You can see like 9 gigabytes, 4 gigabytes. It's split into 2 files. So, you know, it's whatever, around 14 gigabytes in total. So you can see here that it's starting to this is doing supervised fine tuning. I added another parameter here, which is quantizing the weights as well, because that's what QLoRa does. What I typically will do when I'm training is I'll just have a look in NVIDIA SMI to see how it's going. And you can see the utilization is very high now. It's 99% on one of the GPUs. So it's only running on one. I actually have 4 GPUs in the machine. But when I started this effectively, this is a notebook. I didn't ask for 4 GPUs. I only asked for 2 GPUs, right? So I can get in Hopsworks, you ask for the number of GPUs we want, and if they're available, they'll be allocated to your container. So this is effectively my Docker image running here in Kubernetes, and I've got 2 GPUs. So they're shared amongst all the people who have GPUs, but I only see the ones that are allocated to my machine here. So we can see here that, you know, the temperature starts to go up. You can see our GPU goes up to 78 degrees, and it's training. So let me just cancel that. And this is fine tuning. Now, the other one I have I wanted to quantize the weight. So I'm going to reduce the size of weights from 16 bits to 4 bits when I'm training. It means compute takes a bit longer. It's called QLoRa. A lot of the performance results that Sebastian showed in the blog, that the performance is slightly worse, but the benefit is that you've smaller amount of memory used on your GPU. So if you're, for example, training on a commodity GPU, then you probably need to run this Mistral 7. You'll need to run it with this. And the library I need to install for that is called Bits and Bytes. So, you know, I went down here to Hopsworks, and I went to my Python environment and I installed Bits and Bytes. So 0.041. Now you might say, oh, I've installed all these libraries. I now have a Conda environment inside my project in Hopsworks. Every time I start my notebook, I get the same set of libraries. They're all installed, because what Hopsworks does in the background is it compiles a Docker image based on these libraries I have installed. And if I need to do, you know, an apt-get install, I can do it from in here. And then you don't need to write a Docker file. So that's the really nice thing. Your developers won't need to, you know, write Docker files, Dockerize images, upload them to a Docker registry, and then, you know, run your jobs that way. It's all very nice and easy and interactive. You can export your environment as well, so that you don't have to, you know, redo this over and over again like I'm doing this time. So yeah, you can run it with quantized weights. It's pretty much the same. I'll skip over that. There's no point in me running that. And I did actually just run the actual output. So the output here is the chat bot that's been fine-tuned on our alpaca data. Now, it's not particularly beautiful. Like if we go back and look at, I noticed that it doesn't produce spaces in the output, which is a bit annoying. So we go back to our data in here. We have a data directory here. We can see the kind of questions that we had in here. So we had one, give 3 tips for staying healthy. So we can just dump that in as a query into here when it starts. It takes a couple of seconds to start up. So here I can, oh, did I exit? Let's paste it in. All right, I exited the, so it'll take a few seconds. Anyway, so what it does is it prints out the answer, and it's not particularly pretty because I noticed that the spaces aren't coming in here. So while that's starting up, what I'll do is I'll move on to the RAG example. I don't see any questions in the chat, but we'll move on to the RAG example here. So, whoops, now, here we go. Okay. So in the RAG example here, what I have is a data set, which is, it's a very well-known data set in retail. It's an e-commerce data set from a Brazilian retailer called O-List, and it's widely used on Kaggle. So in this case, what I want to do is I want to, let's look at the example. I'm actually running one right now, so let's open it. So I'm running a Gradio UI. What I'm doing here is it's a simple chatbot, and I have no context. So I've added no RAG. There's 0 RAG. So if I ask you a question about the order that I made, so if we go back and look here, I've made some recent order. So in this retail site, I made an order, and this is my order here. I have the order ID to get it. We can see that the order contains some cool stuff. So you could say, does my order or product contain cool stuff, right? And you know, this is an LLM that isn't personalized to me. So it's not going to know. It'll say, it depends on what kind of order you place. I don't know anything about your order. It's not personalized to me. So this is not what we're really interested in. What I'll do is, the reason it worked like that, is I actually commented out this prompt. So this is, what I did was I started out saying, the following is a table with the first row containing the column names and the second row containing the column values. And this table represents my order of a product. So this is my preamble. And then what I'm going to add, so this is the template here. And then I'm going to add this prefix, which is basically I'm using the order ID to retrieve this row here from the feature store. So I'm going to retrieve information related to my orders from here. I've only got one here, and then we can let's just rerun this, restart and run all cells. So it's it's going to add this to my prefix to my prompt. I'm not going to show it in the UI because I don't want to, show this big, long, ugly piece of text. So what's printed out in the Gradio UI will just be what we write there. But it will be sent to the LLM. So I click on this link to open it up here. And we're back to the same chatbot that we had earlier. I'll enter my text. Now it's added information about my product. So if we go back and look here, and I turned on debug here, we can see when I type it in here, we'll see that let's type in a text. Does my order contain cool stuff? And let me press send. So yes, according to the table, the product category name is cool stuff. Now that's not exactly great, but like what we can see is that was entered into the prompt was our preamble here, and then we put in the information about. Now this is very hacky, right? So I'll admit this is kind of me hacking something together quickly, but you can see how powerful the LLM is. It's able to interpret the contents of this, that it's a table, that the first row of the table contains the column names, the second row contains the values, and then it asks, well, does this order that's in here contain cool stuff? And it's able to reason, yes, it does, And then you can continue your conversation here. You can say, what was in my order? And because it's adding that to the prompt as well. We have the history. It should tell me something about what's in the order. And it says, in a not very nice way, the table indicates that the product ID was this, and the seller ID was this, and the shipment date, and so on. So obviously, when you're implementing this in a production system, you might want to have some post-processing that cleans up this text. And another way to do it would be to ask the output to be rewritten to remove all references to the tables, for example. So that's our RAG example of building it. Now we could go back and look at our prompt again. Here, we got our prompt up here. This was the fine-tuned one that we had earlier. And did I have some text? Give me 3 tips for staying healthy. So in this case, this is our fine-tuned one. Now, I mentioned earlier that the space, I have an issue with spaces here, but we can kind of read it: get enough sleep, exercise regularly, eat nutritious diet. And you can see it wasn't super fast, but it generated 27 tokens per second. And you can obviously then try and optimize this and run it on different hardware, and there's different ways of improving the performance there. So that's it. That's the kind of demo. We've looked at fine-tuning a model and training that supervised fine-tuning model on Hopsworks, and we can see that it's stored in here in Hopsworks and everything is available. And then we looked at RAG, so how to implement a user interface that uses, in this case, the feature store to retrieve product ID using an order ID that our application has supplied, and then retrieving relevant information without the vector database. This example, of course, could be improved by adding information from the vector database. I could take the product description, for example, and go to a vector database to find more information about that or relevant data, and you can build the layers of complexity on top of that. So look, Google Slides a bit slow. So this is what we looked at. This was the fine-tuning, and then we had the Gradio example where we asked a question. In Gradio, the order ID was hard-coded into my program, but the user could have entered it as well. We looked up the order ID, we added to the question, and then the model returned a response, and that we showed in the user interface. So what else do you need to consider if you're building these systems? I mentioned in our example, it was telling us about a table, and users don't really want to know there's a table. Evals is Eugene Yan wrote an interesting blog post on production considerations for LLMs, and he mentioned that evals are evaluations. So collecting the clean, fine-tuned training data sets that you want for your model is a differentiator between really good products and ones that are not as mature, let's say. So other things that you might want to do would be look at caching queries that you can do to improve performance, have guardrails, defensive UX, collect user feedback so that you close the loop on this. And I'm sure, as you know, OpenAI are storing all of the queries and all the responses. and using that to further improve their product. Security is also a massive consideration. So there's a very interesting set of top 10 vulnerabilities that are possible for LLM applications by OWASP, who are a well-known security body. Prompt injection, that, you know, if you're allowing people to enter text, as we know from the old days of SQL, many people, when they're first implementing web applications, took the user data and put it straight into their SQL queries, which enable people to attack systems by injecting SQL into their user inputs. So in the same token, you know, we should be careful to sanitize prompts as they come in, and then handling output data. Obviously, if you're training a model and you're using third-party data, you need to be careful that trained data hasn't been poisoned. And when you're serving a model, you know, if it's quite expensive to compute a response, you know, and users are allowed to, maybe you'll have a nefarious user who wants to attack your service, they might be able to do a denial of service attack on that. Then we have other classical kind of security problems: supply chain, the libraries you're dependent on, do you trust them? Supply chain vulnerabilities. And a few other points here that will leave you to read at your own time. So if you're interested in what I've discussed here, and you think you'd like to look at this in more detail, we actually have a Hopsworks LLM lab where we provide up to 25 days of free access, and there's enough GPU available on that lab to, for example, fine-tune Llama 2 or Mistral. Contact sales at Hopsworks.ai to find out more details. Like I said, it's a no commitment access to some, you know, really useful compute to get your hands dirty as such in the LLM space. If you're interested in Hopsworks more, you can join our Slack community. Hopsworks AI has a free serverless feature store that you can use to manage your features for AI as well, beyond what we've been talking about today. So you can use that also as your RAG layer, feature store RAG layer in your LLMs. There's plenty of tutorials out there. And Lex wrote into the chat a link to the Hopsworks AI lab. So it's hopsworks.ai/lab, where you can find out more. We're out of time. Thanks very much. Thanks for the questions during the webinar, and good luck on your LLM journey.